My talk today is on the gaps and challenges in the plastics eco-recycling system, and I'm going to be talking about the sort of forces that are available to us to improve the recycling system for plastics, and it's going to cover where some of the blockages are as well. I'll be moving fairly quickly, but I'm happy to take questions at the end. Just a few words about Nextek. We've been involved in the recycling of post-consumer plastics for the last 17 years, and prior to that in more of an academic and industrial mode. And we get involved in factory design, improvement of processes, and also optimizing the volume of post-consumer materials that are being used in products. But let's have a quick look at where we are if we are working on business as usual. If we continue to do what we're currently doing of making plastics and discarding plastics, we will end up with, by 2040, making 400 million tonnes per annum of virgin plastics. Plastic will end up being 20% of oil production, and we'll have a population of about 9.2 billion people to feed. Now, I'm going to come back to this point a bit later. And we will have quite a lot of pressure on the environment at that stage with the number of people, the requirements for food, and also with the volume of waste that we'll be making. We'll be making 11 billion tonnes of waste per annum. We're doing that in 2021, and by 2040, the leakage to the oceans will be something like 29 million tonnes per annum. Now, clearly, we all want to avoid changes like this, and there's an excellent report called Breaking the Plastic Wave by the Pew Foundation Trust, where you can read these statistics. Now, of course, we are making changes to society and to the regulations around the way we work and the way we consume and the way we dispose materials. And the European Green Deal has mapped out what we would be doing to become climate neutral by 2050. There's a lot of support involved in making these changes, and there are some very big targets to phase out single-use plastics, to reduce waste from where it currently is at 500 kilos per head, the reduction of waste exports, and also improving the circularity of packaging. And of course, the target for recycling of plastics will be 50% by 2025 and 55% by 2030. And of course, taxes or charges to encourage people to move in this direction are already there. And of course, the whole benefit of this process will be to reduce our emissions, to reduce our waste, and to save on unnecessary materials that we would otherwise use. And of course, there could be cost savings in that as well. Now, this graphic that I've got on the right-hand side tells us what system changes we need to put in place and what the magnitude of these systems will be. And you can see on the right-hand side that we've got a change in where we're currently going. The straight line on the graph shows you how many millions of tons we'll be making in waste or in plastics, and where that would end up by 2040. And the big focus of this plot was to say, if we implemented lots of changes, what could we do about plastics to oceans? What could we do about recycling? How much will mechanical recycling take on? How much chemical recycling might take on? And look at what would be the very best thing we can do. Now, this ends up with a whole series of conclusions, which I'm going to go over in a minute. But it clearly means we have to do some things that we're not doing very well right now. So, for example, we would have to double the mechanical recycling capacity globally to something like 86 million metric tons per year. To do that, we have to design products much better. And of course, there'll be a lot of substitution of plastics by other materials. And this is a process that's going on right now. And of course, we're going to have to reduce the growth in plastics production in order to reach some of these targets as well, because as we recycle material, we can displace virgin plastics. And of course, the facilities to process waste will have to be enhanced, not just in countries across Europe and so on, but globally in other countries. And so if we look at where this might take us, if we have all of these positive interventions, we can then look at what might happen. Now, instead of having 26 million tons of plastics leaking to oceans, it could be reduced, in this case, to 5 million metric tons. Now, that of course is still not an acceptable figure, and it tells us that we have to do even more than we're projecting under what we might call reasonable and significant system change. And so globally, we know we're going to have to be very diligent and work harder than we expect to do this. And in this model, you might see that virgin plastic production, instead of being 400 million tons, is about half that, at about 180 million tons. And of course, we can reduce CO2 emissions, and we can actually create jobs in the recycling sector as well. And of course, all of these changes have been based on technologies which are readily available to us. Now, coming back to some of the things that are driving our planet, one of them is the growth in population. And as we've mentioned, we'll have over 9 billion people by 2040. And linked to that, we also are seeing, again, countries where people are being undernourished. And we've seen, instead of a decline, a slight increase from 2016 onwards. And we're seeing something like 800 million people being undernourished. Now, if we look at that situation and also look at the scenario of food waste is a global phenomenon, and it occurs when we, first of all, grow products in agriculture, and food is lost due to either poor harvesting or poor storage, or it's lost after people have processed the food. But globally, we're losing something like 30% to 33% of the food that's currently grown. And of course, what that means is we're using a lot more water, using more land, we're using more fertilizer, we're using more energy. And if we can minimize food waste, then we will actually be able to emit less CO2, be able to feed people better, and this is a much more positive outcome. And here's the link to plastics. Plastics and other packaging formats are key ways of reducing food waste in developed and developing economies. And this is really a key role for plastics. And so we know that in order to feed the populations that are coming, we will still need to use efficient materials. And of course, they have to be carbon efficient as well. And plastics are both. So it's inevitable that we will continue to use plastics, but that then puts the pressure on using those plastics in a much more sustainable manner. If we have a quick look at where the world produces material, we currently make something like 1 million tons of plastics per day globally, and around about 58 million tons in Europe. And 51% of the world's plastics production is based around Asia. And of course, so no matter what we do in Europe and also North America and other developed countries, the majority of the impacts of plastics, whether they are used well or not well, will happen in Asia. And indeed, this is where a lot of the concerns are. So a lot of the comments I make have to be applied globally. So what is happening right now? We are seeing what we call a global plastics crisis, driving retailers and brand owners to take responsibility for the packaging that they're making. And now we know that we've got many commitments to use recycled plastics. And of course, to use recycled plastics back in packaging, it has to be high quality. And so we need to have very good materials coming back through the recycling process. And of course, if they have to be high quality, we have to make sure that the designs are right and the technology for recycling is right. And this is really where some of the innovations that we'll be discussing can help unlock the potential of these materials so they can be reused with low carbon impact. So what are some of the blockages to the circular economy? Most plastics have been made for only one cycle. When you think about all the products that are currently on the market, they haven't necessarily been designed for recycling, even though the material could be recyclable. Many products are brightly colored with pigments. This means that when they come back for recycling, it limits where those products are acceptable for reuse. So maybe we should be talking about many more plastics without pigment. We're also seeing multi-layer materials, which makes recycling more complex. When we have materials that are not compatible, where we have high melting points married to low melting points, those materials may not be recyclable. And so mono materials are preferred for design. Food grade recycling is very difficult in Europe. It's also difficult anywhere in the world. And there needs to be greater focus on the capabilities within the recycling sector and the regulations we apply to food contact materials. That's a very big topic. Here, my last point on this slide is that if we do the very best on collection and we do the very best on sorting and the very best on yields in recycling, we will potentially recover 60% of what we put into the process. This means that we'll still always need virgin plastics, and it also means that the way in which we put recycled content into packaging should perhaps not focus on 100% content, but maybe other areas as well. So let's have a quick look at the materials that we use in the packaging sector. This chart is from Plastics Europe, and this is the 2019 figures. You can see here on the right a circle for PET. There's one for polypropylene, high density next, and then low density. So you can see low density polyethylene is the most widely used material in packaging, and then high density and PET and polypropylene are very similar, but the next big one is polypropylene, and then PET and high density about the same. So if we ask the question, can we recycle the biggest polymer that is currently made for packaging? Well, the answer is it's challenging. And can we make it into food grade? Well, the answer is currently we're not doing it. There are some technologies coming up that may be able to do it. Polypropylene is the next big one. Can we recycle PP, pot stubs and trays? The answer is yes. Can we make food grade? It's possible. I'll be talking a bit about that in detail later. For PET, can we recycle those materials? Yes, we can do it, especially for bottles. We've got food grade. It's very much a simple process. Thermoforms, well, that's a little bit more interesting because there are not many thermoforms that are being recycled back into many other products. Are they food grade? Well, there's an interesting question because there's some question marks about the way thermoforms are actually made with recycled content in the mid layer. HDPE, can we recycle these materials? Yes. Can we make food grade? Yes, these are on the market. And of course, this means that we can create circular markets for those materials. So they're the big ones. If you have a look in the middle here, there's a small circle for polystyrene. It's much smaller one for EPS and a small one for PVC. So in the packaging sector, the ones that we've been talking about are the big four, and they're probably the materials that are most likely going to be the materials to be for packaging to be made from and to be recycled. And you might notice that about 40% of all plastic production is being used in packaging applications. So what do we currently do with plastics at the end of life? Well, the biggest application for end of life is in waste to energy. So we are still probably at the moment sending something like 12 million tons to energy recovery. And recycling has been growing steadily, and we are now at around about just under 10 million tons of recycling in Europe, and with the landfill falling lower and lower, typically at the expense of those other two technologies. So we are heading in the right directions, but waste to energy has a big penalty because it does create CO2 emissions. And now we've got very clear targets for carbon neutrality by 2050. The concept of waste to energy will need to be looked at again because plastics still are a big part of that waste. And of course, that means we will need to decarbonize waste to energy, we'll need to take the plastics out, which means we need to recycle more. So here are the sort of comments from different brand owners like Coca-Cola, McDonald's, Unilever, PepsiCo, Evian, and many others. They've all put their commitments to say they want recycled content. So where are these companies right now? Well, in 2019, a number of the companies signed up to the Ellen MacArthur Foundation New Plastics Economy, gave a progress report of where they're up to relative to their targets. And if you have a look at these companies like Nestle, who committed to 65%, well, they are at, that's a 2018 target, and that they are meant to be at a much higher level at by 2025. Well, they're only at around about 2%, and their 2025 target is 15%. And if you look at a company like Pepsi, they're at 3%. Unilever, they're at 1%, even though they're going to 25%, and so on. Now, my point about this is that companies are making strong commitments. They're on the start of the journey. There's going to be a big pressure for them to actually start recycling and start using recycled content. And indeed, they are all doing it. We know that they are, but it means that there will be big pressure. Now, part of the process of doing this is now being driven by the Plastics Pact concept. And so there are national plastic pacts in Europe. They're also in South Africa, United States, in South America, and new one in Australia. And they're all very common. They all take the approach that they'll have commitments to make packaging recyclable or reusable or compostable, with targets by 2025 that 70% of plastics packaging will be effectively recycled or composted, with 30% recycled content across all plastic packaging, and also a comment to eliminate single-use plastics. And here are the targets by, in this case, Australia, UK, and USA, all very similar. Some of them are a bit more adventurous, but this is, if you like, the global mechanism that is starting to drive industrialized countries to target the recycling of their packaging, and this is part of their roadmap. So when it comes to recycling, well, how recyclable are many of the products? And as we've been discussing, many resins should be ideally unpigmented, but many plastics are highly pigmented. So if we take the simple area of caps on bottles, they're often used as a final color for a package to identify a product, but ideally, we should try to make those in a natural color with no pigmentation, and they should stay with the bottle so we don't lose these fragments which could end up in waterways, and also they could then be a recycled component. Labels on packaging, which are very often seen, well, they need to be also easy to remove and not contaminate the recycling stream. Adhesives and glues, often the forgotten part of a container. The glues can go into the recycled material and create problems in recycling. Now, by June 2024, the European Union has mandated that caps will have to be tethered to bottles. And here are some examples. So those bottles will then bring the cap with it into the recycling system. And some companies are already moving ahead, and they're making labels, bottles without labels, like the Evian bottle still has a pink cap, but the water bottle on the right has a pigment-free cap and a very simple label which comes off very easily with minimal adhesive. So these things are good examples of which way to go. In cases like polypropylene pots, tubs and trays, we still seeing lots of pigmentation. We're seeing in-mold labels on the outside, even though the polymer is largely natural in color. And we're seeing opacity requirements. So this is an area where if we're going to hit our recycling targets, we need to think very carefully about the pigmentation in these materials. Now, in the collection of materials, we use many systems for the collection from community to community, from country to country. And obviously, this is a key factor in getting packaging back so we can actually recycle it. And this is really where we need to have a focus on having the big four polymers, PET, high density, PP, and low density as the main packaging materials. When you see two products like we have on here, we have a PET container and a PLA container. Now, consumers can't tell the difference, and the PLA container might be a bioplastic, and it could be industrially compostable, but it's not going to mix in with the PET stream. So we need to think carefully about making good choices in packaging and good choices in materials so that they are compatible with the collection system. So when we close the loop on plastics and packaging, we also have to think a lot about what is it that's acceptable on a supermarket shelf. Brand owners don't like to see color variation. And if you look at the image on this slide, every second bottle has 25% recycled content, and it's been pigmented, so it looks close to the finished, the virgin material. Now, I can see the difference between the bottles, but will the consumer worry about that color variation, and would they accept a small variation given that it contains recycled content? Now, some years ago, the answer would have been no. These days, the answer might be yes, but ideally, if we're going to have higher levels of recycling, we should be looking at the absence of pigments or standardize on pigments like natural or white, so that we can actually recycle things into very clear applications. And another way of looking at how do we deal with the colored packs that we have today. If we mix them all together, we end up making a gray, and here on the left you can see what 30 to 75% recycled content in high density looks like. But these products are always sold with a sleeve on them. And so here I've shown you the products with a sleeve, and they look virtually identical, except for one small part of the container where the sleeve meets the top. So is that a possibility? Should we be looking at this? Will brand owners accept approaches like this, which allow them to use colored materials? Certainly, this would open up much more market for recycled plastics that are currently made in that particular way. So the next comment here is the quality demands for recycled plastics. Right now, the quality demands for recycled plastics are very stringent, especially if they're going into a large brand owner. They want these materials to be completely toxic free, they have to be free of odor, and they have to have consistent properties. And this can be done, but it requires high quality control over the inputs, over the recycling process, and also monitoring the final products. And so it can be done, but doesn't mean it's easy. And that's a challenge. And just a few words about mechanical recycling. This is the image I'm showing you here is what's fed into a PET recycling plant in the USA, where this is really quite problematic material. But this is really what some recycling plants are offered when it's meant to be PET. And of course, this creates all sorts of difficulties in recycling. So collection is really quite important. Sorting is super important. But just to say a little bit about mechanical recycling, because this is really where most recycling is done in all parts of the world, where materials are collected, they are sorted into single streams, so high density into its own stream, PET into its own stream. These materials are ground down to smaller particles, they're hot washed, they're color sorted to remove strange colors, and then they will be reprocessed by extrusion and potentially decontaminated for food contact applications. And then they'll be offered for conversion into products. So just a few words about these. I've got a couple of images of what recycling plants look like internally. They're full of mechanical recycling operations for grinding, washing, for extrusion. And these systems are readily available. They can be installed globally. They can be applied to the 4 big polymers. And so we do have the means to recycle more mechanically. And I make these comments now because we'll be talking a bit about chemical recycling a little later. So the circular economy challenge for flexible films. You remember we talked about films being the biggest, low density polyethylene being the biggest polymer made. And of course, it is the big challenge because these materials are thin. They're quite difficult to handle. They can be multi-material. And of course, there's a big move now to go from multi to mono, or at least compatible blends. And of course, there are many colors, which means we end up with colored products at the very end. And many of these have an odor associated with them. Now, on films in the United Kingdom, we put something like 400,000 tons of films onto the market, and only 4% of them are recycled. And this will be comparable to many other developed countries. And so films is the one area which is going to be a big challenge for every country. And films are the material that are most likely to end up in the environment as well. So this is really where we have to put a big focus on recycling. Food grade high density polyethylene, well, there are examples of this already commercially in the market, and they have been operating in that market for 14 years. The input for, in this case, milk bottles has to be 99% food grade materials, and that allows the material to be turned into very clean materials that meet food contact requirements. There's a lot of controversy about this. So, now, in the case of polypropylene, here's some examples of polypropylene that have been recycled back into food contact applications. This is an area that's been put aside for some time, and remember, it's probably the second biggest volume packaging material, but because it's not a bottle and made into pot stubs and trays, it hasn't had the same attention for recycling. And to make food grade, there are some special problems of separating food from non-food prior to the recycling process. So, quick comment about polypropylene. You can see from the bar chart on the right, polypropylene is the third bar, so it's over here. It's by far the biggest polymer that's being used in Europe for its total volume. In packaging, it's about the same as the others, but it's a very big material, one that can be widely used. So 10 million tons in Europe, and globally it's about 83 million, about 60 million tons right now. And what that means is it's a big part of the volume of the global production. So, and yet polypropylene is one of the least recycled materials. So we have developed a project called Next Loop, which is all about recycling polypropylene back into food grade. And the driving forces are the European packaging charges of 800 euros per ton for packaging that does not contain 30% recycled content. United Kingdom has a £200 per ton tax on packaging that doesn't have 30% recycled content. So these will be the driving forces that will encourage the adoption of food grade recycled content. Now, why has polypropylene taken so long? Well, the first step is you need to be able to sort materials from non-food into food grade, and then you need to be able to decontaminate them. So the technology that we have developed has been to use fluorescent markers, and you'll see here labels that under ultraviolet light change color and they fluoresce in a unique wavelength of light. And we have a library of colors that we can use, And the coding of the fluorescence allows the bottle to be identified as a food grade or a non-food grade, or a black, or it could be applied to a clear sleeved bottle of PET. And of course, what it means is if you have these markers on a package and you can use the conventional recycling systems and reach greater than 95% purity in the first sort. So you can separate food from non-food at high speeds and get high purity. And if you do it twice, you can get greater than 99% purity. And I've got a very short video to show you this at work, because a lot of people don't appreciate how recycling occurs. And this shows bottles that are sleeved, and these are PET bottles, but the focus will be the same for all materials. And you can see the sleeve bottles with the markers being mixed with other waste packaging. And here you can see the sorting going on. It's done automatically by camera identification and air jet ejection. And this happens very, very quickly and very completely. And you can see on the right, the reject fraction, and on the left, the accept fraction. So very high levels of separation. And this allows packaging to be classified into new categories. So the combination of those two steps of the separation process and the decontamination process allow us to create food grade material. And these are the sort of things that will be happening. There's post-consumer packaging, and on the right, the products that can be made from the food grade material. And that really starts a whole new circular economy for polypropylene. But there's a warning here. Everybody wants to use high levels of recycled content. And on this table, I've actually modeled what will happen if we use 50% recycled content with each pass. Now, as we keep on using a package with 50% recycled content, on the next pass, 25% will have been used, gone through the cycle twice. And if we keep on going, you will see at 50%, we will have 12.5% of 3 cycles, 6% of 4 cycles, 3% of 5 cycles, and then 1% of 6 cycles. Now, what this means is, as the polymers get thermally stressed through each cycle, they will undergo changes in color and perhaps molecular weight or molecular weight distribution, which will limit the usability of these materials. Now, this comes back to the point I made earlier of designing plastics to be recycled for large numbers of cycles from the very beginning, which makes the process of being recycled more resilient through each cycle. So this is the warning. And of course, if we go to 100% recycled content, every material will have multiple cycles. And so we'll rapidly see a change in composition. That's why 100% is not technically sustainable. So what this means is everyone's looking to use chemical recycling and to see whether they can actually recycle these materials in some other way. So PET is ideal. It's what we call a condensation polymer. We can break it into its components into monomeric species, terephthalic acid and ethylene glycol. And there are a number of companies doing this. And there are, of course, that's for PET. For polyolefins, the low density, high density polypropylene, they don't behave like PET. We can't use the same sort of technology, but we use thermal cracking. So thermal cracking actually randomly cuts up the molecules, and this material turns into an oil which can be fed into a refinery. The refinery then can actually take out the naphtha component. It will then have the bottoms. Well, what it means is whenever you make an oil out of polyethylene, not all of it goes into the oil fraction. Some goes out as gas, some goes out as a tarry material. So you don't get 1 ton in, 1 ton out. And so the energy footprint is also high. Now, the world is hoping chemical recycling will be developed on a big scale. and it needs to be run on a big scale. And we're only seeing the very beginnings of this. Well, and these plants, if they're going to really work, have to take in hundreds of thousands of tons of material that preferably can't be recycled, because recycling has a lower carbon footprint, and we have to look after that. So this is really where the limitations are for chemical recycling. Big capital, big collection, lots of processing, and not a great carbon footprint at the moment. So should we be turning to bio-based and biodegradable materials? Well, this is very much a big topic right now, because some people are looking to biodegradable materials to solve the problem. But what actually happens to these materials? Some bioplastics are just like polyethylene or polypropylene, and because they're made from sugarcane, which gets turned into monomers. These bio-based materials have to be recycled in the same way. Even though they're made from sugars, they are still like a conventional hydrocarbon. So they won't degrade. The materials that do degrade can be made from either petroleum or they could be bio-based. Now, the challenge here is this the right direction that we should go into? Because the ones that are degradable are generally not easy to recycle. And this means that we have challenges. So here is a tray made from PHBV, which is one of the best materials for biodegradation. So when you make it into a film, it'll biodegrade quickly. If you make it into a tray, in this case, we were monitoring this for nearly a year before we saw significant degradation. So yes, it will compost at ambient conditions, but will take time. And how much tray do we collect over a year? And of course, the end result is this material ends up as carbon dioxide and water, and we don't have any result to show other than the fact that it's disappeared. And that may be a good thing when it's lost to the environment, but if we can control collection, then maybe we should be recycling. And in big cities, where will our bio-based and biodegradable materials end up? Well, almost certainly, if they're collected in big cities, they won't be recycled, but they'll inevitably go to incineration, or they may go to biogas and composting if the facilities are there. Right now, those facilities are not widely available. So bioplastics represent an interesting area, but again, we haven't developed the infrastructure to properly invest in them. So the bigger opportunities are the building of large-scale recycling operations, which can actually take materials and recycle them, hopefully efficiently using modern techniques. And this is a plant that Viridor are building and will be in operation later this year. I'm coming to the end of my presentation. And I just want to say, what is it that we need to do? What are the challenges ahead of us? Well, clearly, from my point of view, the biggest challenge is to make everything designed to be recycled, hopefully back into the same product that originally it was made from. Not downcycling, but keeping it at the same level. So food packaging to food packaging, non-food to non-food. And of course, also trying to avoid the loss of materials to waterways and to oceans. And this means it puts the focus on what is actually happening globally, not just in Europe, but especially in developing countries where they don't have waste management. And so if they had waste management, we could actually do something about it. And of course, this is really where brand owners need to put products on the market in those operations where they can be coped with. And so hopefully we can actually implement the right technologies in the right countries at a very fast rate. That's our big challenge. But my final point is, if we can imagine a solution like how do we get to Mars and how do we put a helicopter flying over Mars? Well, then we can do that for plastics. So my comment is every plastic can have a circular destiny, and that's our job. And I'm sure everyone's going to support going in that direction. And